We've spent centuries peering into the dark, trying to pull the absolute edge of the universe a little bit closer. And to do that, we've built some truly incredible machines. Take the Hubble Space Telescope. It proved supermassive black holes exist at the heart of galaxies, captured the first collision between astronomical objects, and even found water vapor on distant worlds. Then there's the James Webb. It is a true engineering monster. With a mirror 21 feet across, it resolves details 600 times sharper than the human eye. At that resolution, you could read the pattern on a coin from 25 miles away. Or the Event Horizon Telescope. By syncing up instruments all over the globe, this network managed to image the swirling gas around a black hole with such precision, it could spot an orange sitting on the moon. But even with all of this hardware, if we point our best lenses at a nearby exoplanet, all we get is a handful of blurry pixels. To actually see continents or oceans on another world, we'd have to build a glass mirror the size of a small country. Fortunately, we don't have to build one. Sitting right in the center of our solar system is a 4.5 billion-year-old lens. It's 109 times wider than Earth, measures 864,000 miles across, and it is entirely free to use. The sun isn't a mirror or a glass lens, obviously, but it is incredibly heavy, and as Albert Einstein figured out, heavy objects literally bend the fabric of space and time around them. Think of it like dropping a bowling ball onto a stretched-out bedsheet. The fabric dips down around the weight. If you roll a marble past that dip, it won't travel in a straight line. It's going to curve. The sun does the exact same thing to passing starlight. As light from a distant exoplanet grazes the sun, gravity bends it inward, converging at a specific point in deep space. Astronomers call this gravitational lensing. To use this natural magnifying glass, all we have to do is place a camera right at that focal point. But there's a catch. That point is located 542 astronomical units away from the sun. An astronomical unit, or AU, is the baseline distance between the Earth and the sun. To put that into perspective, 542 AU is roughly 13 times further out than the orbit of Pluto. It is more than 3 times further than Voyager 1, the most distant human-made object in existence, which has been traveling through space since 1977. Harnessing the sun's gravity requires pushing the absolute limits of human spaceflight endurance simply to reach the viewing angle. Even if we make it out there, we face another massive hurdle. The focal point isn't a neat, tiny dot. Because the sun is so large, the focused light is smeared into a huge patch tens of miles across. Plus, the exoplanet we want to look at is moving. If we send one giant Super Voyager probe to fly through that massive focal area, we'd only catch a minuscule sliver of the light. It would be like looking at a single pixel of the Mona Lisa and trying to describe the entire painting. To get the full picture, we have to map the entire target area. The current proposal solves this by ditching the single giant spacecraft entirely and instead sending out a synchronized swarm of tiny ships to work together. But this creates a propulsion paradox. Tiny spacecraft still need instruments, power, and fuel. Loading them up with enough traditional propellant to reach 542 AU makes them too heavy to actually be tiny. The answer might be solar sails. Instead of carrying dead weight and fuel tanks, these ships would launch from Earth, unfurling malic sails to catch solar radiation pressure, literally allowing the physical push of sunlight to accelerate them. Operating like cosmic sailboats, this swarm would constantly accelerate outward, building up insane speeds and cutting the travel time to the focal area down to just a few decades. Once they arrive, the real work begins. The swarm carefully maneuvers into a grid formation, sweeping across the huge focal plane. Each tiny ship collects its own slice of light and then beams that data back to Earth so we can stitch the full image together. By replacing heavy chemical fuel with the wind of the sun and swapping a single massive mirror for a coordinated robotic swarm, this theoretical physics trick actually becomes a viable mission profile. Right now, there is a gap between this blueprint and our capabilities. We don't currently possess solar sails that are efficient enough, or spacecraft swarms that can autonomously coordinate at that extreme distance. But those are engineering hurdles. They aren't unbreakable laws of physics holding us back. And the reward for solving this puzzle is staggering. If we aimed this system at Proxima b, the nearest exoplanet to our solar system, we could achieve a surface resolution of nearly 1 mile. This system captures the actual topography of an alien world, mapping mountains, oceans, and continents on any planet within 100 light-years. The next great leap in astronomy doesn't rely on building ever larger glass mirrors here on Earth. It relies on mastering the mechanics of the cosmos and turning our entire solar system into the ultimate interstellar observatory.